is going to lead to a free response question that's on there every single year. Before, the opinion was this was the most difficult free response question of the 6 questions, right? I think some teachers have drawn back on that because there's a way about this question, and usually now they give a question that nobody can really plan for anymore. It's just very almost experimental to some level, and we'll talk about that eventually as well. But let's go ahead and get started. So the other day I showed you guys a function which says g of x is equal to the integration from 0 to x of t dt. And so this is called the accumulation function. And the accumulation function, essentially what it says is whenever you want to change this top limit, basically you're going to change how much area you pick up, all right? But then it leads to a second conclusion using the fundamental theorem of calculus, is this must equivalently be true. Now I shared those things with you on Friday, so I'm just repeating myself. And finally, the third thing that we realized is if you were to take a derivative of that derivative, you'd end up with this situation over here, all right? So I want you to think in terms of modes, all right? Think in terms of modes. When we're going through this lesson, basically one of them is always in a different mode than the one that's right next to it, right? Like for instance, Idris, do you have a younger sibling?
Yeah.
You have a younger sibling? Okay, how old are they?
6.
Okay, they're 6, all right, and how old are you?
16.
You're 16, okay? Hey, happy birthday, by the way. Yeah, I saw the little cake next to your name today. Yeah. On Friday, it's the sweetest thing ever, you know, Yusuf. So there was a boy in the senior class, and he's like friends or maybe cousins with another boy, and so he brought him a surprise cake. That's sweet. Yeah. Well, he got permission from me in advance, and then the kid was totally unsuspecting of it. He was just sitting there, and then the other kid walks in. He had asked for permission. I didn't know he was gonna bring such a large cake, you know. And he brought it.
We ate the cake.
Hey, you were there at the party.
Oh.
Yeah, I remember you there. Yeah. I like how you guys walked in and you're like, oh hey, there's cake. And like, yeah, that's why you came here. I never seen you here before.
No, I thought you brought it for himself. I didn't think so.
No, that was a birthday.
Yeah, I saw him upstairs.
Yeah. So, oh, you were there too.
Why didn't I get invited? What period? So first period. Oh my goodness.
It seemed like a basketball team thing.
No.
So, because I saw Dina there too.
She saw us there.
And then they were talking about sports anyway. So, where's your cake, man? Tomorrow?
You showed
He
it.
said he didn't forget.
Alright. Anyway, so what was I talking about? Yeah,
Idris
so Idris has a little sister. She's 6 years old and he's 16 years old. That's what you said, right? So when she turns 7, right? You know, approximately, what will Idris then turn after 17? You see, as soon as one person switches a mode, the other one also switches a mode too. So that's kind of how you want to think about these functions. Whenever you're talking about a certain function called f, that's like Idris's little sister, okay? That's a different function, but that function will go through modes. Then this right here is kind of like Idris, and he will go through his own modes. And one is always going to be lagging behind the other. They will always be like that. It'll always be the relationship. So for instance, when you're finding the area of the f function, you're just finding the value of the g function. When you're finding the value of the f function, you're actually finding what's the derivative stand for? The slope of the g function. When you're finding the slope of the f function, what are you really finding on the g function? So that's the relationship. One always lags behind the other, okay? They will never ask you for a g third derivative, because if you think about that would lead to a second derivative of f, so therefore the concavity. They don't tend to really ask about that part right there. I've never seen it ever.
Awesome.
Okay, now, yes?
When when you have the like third derivative or fourth derivative, like what does that represent on a graph?
It's really hard to say on a graph what that might be. You know, you can't really see it. You would have to like kind of zoom into the part of the graph where you're looking beyond just the concavity. It's the change in the concavity, whatever that means. Okay, so can't really visualize it. But in physics, I was telling them that like position is the function, velocity is the derivative, acceleration is the second derivative, but then there is an application to the third derivative. It's called a jerk. Okay, so as soon as somebody presses an accelerator, there is, let me get this straight, there is a rate of the rate of change. So it's, again, it's hard to like visualize without it. It's very small, but it's, I would say it's that feeling that you get in the back of your neck when suddenly you do kind of like jerk behind when somebody accelerates. If you've ever been in a car where somebody did that to you, it hurts. Okay, what I want you guys to do is I want you to make the same graph on your notebook, and please give some space on top. I always tend to forget. Give some space on top, so we'll be putting some bars on the graph as well.
How many the lines are you putting?
You're gonna need 2 bars. Okay. You're gonna need 2 bars of that. Now the numbers are important. So you see where the peak is at 2, and another one, the trough is at 5. Those things we need before as well. Mine is a little exaggerated. Okay, now, it becomes super important that you label what the graph is reading, because there's gonna be 2 functions, and to each function you can have 3 modes. So you gotta figure out what you're looking at before you start, right? So this right here, make it a big deal in your notebook. This is the graph of f. Alright, this is the graph of f. We'll come back and we'll kind of relabel this as if you're a graph of f, then what must you also be? Now at the top, you want to make 2 bars. Now on these 2 bars, what you want to do is you want to go ahead and write down for the first bar, g derivative is equal to f. And on the second bar, write down g second derivative is equal to f's first derivative. Alright? So whenever they give you these graphs, they're never going to ask you about f. That's kind of useless. If they wanted to ask you that question, that would have been pre-calculus. Okay, so they're not going to ask you things about f. You want to jot that down. Alright? They're not going to ask you about the graph that they just gave to you. However, you will be asked about the graph of G. So the graph of G, what you need to do is understand, according to the second fundamental theorem of calculus, which I have now taught to you 2 times, if this is the f graph, it's also the G derivative graph. So suddenly what you're learning in this lesson is the same thing as what you learned a few lessons back, which was called reading derivative graphs. So remember, you're not reading the derivative graph of f, you're reading the derivative graph of g. That's really what this thing actually is. So having said that, let's go ahead and read this like a derivative graph. If we read this like a derivative graph, it's not too long ago, you just took a test on it on the last week. Where would you first mark this? What number is important?
2.
Sort of.
Wait, is this the graph?
Wait, which one are we
I thought
doing?
it was after it. Not after it.
Alright, so listen to my words again, alright? This is the graph of f.
Also,
I'm not asking you about anything about the graph of f. We're going to be answering questions about g. So if the graph of f is truly the same thing as g derivative, again, according to the second fundamental theorem of calculus. So f is the g derivative graph. So we're gonna read this like a derivative graph, okay? So let's go ahead and start again. There you go, you're gonna go ahead and mark this at 4. Mark this at 4. Okay, all of this right here is positive, and then after that is negative, so go ahead and mark those things. Now, mark the 2, mark the 5. This is gonna be positive, and negative, and positive. Alright, so I want you, by the end of this lecture, to say, oh, okay, this is the same thing as before, it's just a small little thing that we need to basically make up for. Do we have to mark the 4? Yeah, we marked it up here, right? Alright, now, remember, the conclusions that we're gonna make are always gonna be about G. Okay, they're not gonna be about F. No one's gonna ask you about F because it's literally right there. So the conclusions are about G. So write these down. Yes. Okay, let's start with the first one. On the graph of G, where would you guys say the critical points should be? Okay, so write down, there is a critical point on the graph of G at x is equal to 4. Now comes the reasoning, because all of these are going to come with a question that's going to prompt you to tell us the reasoning. So what's the reasoning? Not quite, because G derivative equals 0, right? So here's the only difference between doing this before and doing this now. Before you would have just said G derivative equals 0. But what you need to do is add a little bit more in there. Write down that G derivative, which is the same thing as F, is equal to 0. You insert that little piece in there to say that, look, I understand what you actually gave me was a F graph. I get that. You gave me a graph of F. But with my understanding of the second FTC, that F graph is the same thing as the G derivative graph. So if you ask me questions about the graph of G, then I can tell you things about the graph of G, and this is the first conclusion that you make about the graph of G. Okay, now let's talk about that critical point, alright? That critical point is a what? Is it a maximum? Is it a minimum? Is it neither? What is it? Alright, if you go from positive to negative, that must be a maximum. So write down, there is a maximum, or should I say a relative max at x is equal to 4 because, now before, what was the reasoning that you guys used to say why there were maximums? Okay, what switches signs? The derivative, right? So you're going to say the same thing again. You're going to write down because G derivative, once again, because it's equal to F. You have to keep making that connection. That's the only update that you need to make from when we used to learn this before. There's a relative maximum at x equal 4 because G derivative is equal to F. Switches signs from positive to negative. One of you on your test last week, you wrote almost like a short story about the reasonings why you think this so. Please don't do that, okay? You're making things unnecessary, and I'll tell you right now, math teachers have a very short fuse. They just get annoyed and then they mark things wrong even though they're correct. Okay, I'm talking about the AP, I'm not talking about myself, right? So just be mindful of that. Okay, so there you go. We got all of that cleared out for the first one. Now let's talk about inflection points, okay? So write down, okay, how many inflection points do we have here? 2, alright? So write down, there are inflection points at x is equal to, go ahead, 2 and
5.
and x is equal to 5. I'll keep reminding you that we're talking about the graph of g. I know I didn't write it over there because it's kind of attached to that previous statement, but I don't want you to start thinking that he's talking about the graph of f. We're not talking about the graph of f, we're talking about a graph of g which is not shown here. So on the graph of g. Okay, so let's go ahead and talk about the reasoning. Why did we used to say things were inflection points before? What switches signs? The second derivative, right? So write down because g double derivative, which is equal to what then? Beautiful job. So this is the part, I keep putting it in red because it is the thing that's gonna bother you and you're gonna tend to forget things in the beginning that way. So because g second derivative is equal to f derivative, switches signs there. A lot of you spent, this is why you ran out of time, by the way, on the test, because you overwrote things, okay? I kept telling you, look, just be succinct, say these things, and move on. And then the reason why you didn't get to that last page for some of you is because you're just writing too much, right? I don't need to hear from you that positive means above and negative means below. When you say that to us, we trust you for what you're talking about, right? So because g double derivative is equal to f derivative, switches signs there. That is it. You don't need to tell us what it was before and what it was after. That only applies for when you're specifically talking about maximums and minimums, okay? Yes?
Why are we talking about the graph of g?
Because that's what all the questions are going to be about, okay? About the graph of g, not the graph of f. If you wanted to ask somebody questions about the graph of f, that would have been pre-calculus, okay? It's all about the graph of g, a graph that's not shown to you. So what I keep telling you, and I'll keep repeating this, the graph of f is the same thing, not as the graph of g, but the g derivative graph. So read that like a derivative graph of g, understand? And you're making conclusions about the g function, okay?
Is it a position graph?
Is this a
That's
position?
velocity.
Well, okay, if we're gonna talk about it in terms of applications, it doesn't help to think of it that way, but the position graph of f is the same as the velocity graph of g. So it's like reading a velocity graph, think of it like that, okay? Alright, now let's talk about the increasing and the decreasing, and let's talk about the concave up and concave down, right? I'm gonna shorten this a little bit because I know that you guys are quite accustomed to it. I'm gonna write down g is increasing on, alright, what are the intervals that g is increasing on? 0 to 4, because, that's okay, it takes some time, because g derivative, which is equal to f, alright, oh no, you just said it, is what? Is positive. That's it, okay? Alright, really quickly follow up with where g is decreasing. Obviously, I don't get time to do this every single time, so make sure you're just kind of writing all this down, and then in the future I'll have you guys also writing these 4 to 6, because,
G derivative equal to f.
yeah, remember, never say f, and never say it. It, we don't know what it is, there's too many things on the board to be calling them it. So, there you go. Alright, let's talk about the concavity. So g is concave up on 0 to 2, go on.
And 5 to 6.
5 to 6.
Because g derivative equal to f derivative is concave.
Exactly. Alright, go ahead and close up. Write down where it's concave down real quick. I'm sure you can do this one by yourself. would be, 2 to 5.
Yeah.
Alright, real quick, the reasoning is,
Because G derivative, double derivative is equal to F derivative.
alright, now, a popular other option that the AP uses is to say, whenever you wanna talk about G second derivative being negative, you're allowed to say G derivative is decreasing. I repeat that. Whenever you wanna say G double derivative is negative, you can say G derivative is decreasing. You are saying the same thing. Now, if you're wondering which one do they prefer more, they actually prefer the other statement more. They like to hear that you are talking about G derivative decreasing, right? But they can't mark it wrong if you write it like this, alright? Alright. So, this is a very tough question, and there's no easy version of this, unfortunately. I made this question up to help you. After this, we just jump straight into AP problems, okay? So this would be one of the first AP problems that we'll be dealing with. Alright, so what you guys wanna do is make a nice graph in your notebook. We're gonna be on this for, I think, through tomorrow. Put the graph into your notebook. And as you're putting that graph into your notebook, there's a few things that are mentioned in the beginning part that you have to make sure that you jot them down as well, okay? You can't miss out on them. Like for instance, it says it is known that the point 3 comma 3 minus root 5 is on the graph, stuff like that, okay? This was, I think it was the 2019 or 2021 question. It's very difficult, very, very difficult. Yes.
If I have this much space, should I start anything?
Yeah, you should probably start. I mean, this is gonna go through tomorrow, like I said, so if you wanna start new pages. Alright. Yes, so whenever we're doing this lesson, it's probably just best, even if I tend to forget things as usual, just make space for the bars. All those numbers are super important. You're gonna be finding areas in this question too, so you make a good graph. Alright, I think we're about ready to get started here. So I don't need you to start reading the graph right away. That's not actually what the question, will come around to that question in a little bit. So this says this is a continuous function, and please make sure that you label that this is the graph of f. Remember, they're pretty much always gonna do this to you. They're gonna give you a graph of something. They're not really gonna ask you too many questions about that same graph. They're gonna move on to the next mode. The initial condition is for the graph of f, it says it goes through 3 comma 3 minus the root of 5. I want you to just take a minute, find that point on the graph here. Okay, look at where 3 is on this graph. And notice how it's not going through some nice number, like for instance 2 comma 3, that's a nice number right there. This one is going through something, so they're telling you what that something is. It's 3 comma 3 minus root 5, that's what that means, okay? Okay, so go ahead and write down the first question. The first question says, if we were to tell you that the area from -6 to 5 of this graph that we have given to you is equal to 7. So you're given this piece of information. It says, could you tell us then what is the area from -6 to -2 on the same graph? So what happened this year is, again, most students were expecting that they would give you all of the graph in order to work with the graph. Unfortunately, this graph is only given to you from -2 to 5, yet if you look at that first fact that they've stated, they talked about -6. In other words, there is a piece of the graph that's here, but they didn't give us like the actual graph itself, okay? So that was one of the problems, it just threw everybody off. They're like, you know, I didn't see that sort of coming. But they did mention up here that the graph of f is good for -6 to 5, even though what's displayed is only from -2 to 5. So automatically, it's a bit of a problem to be thinking about something that you can't actually see here, okay? All right then, so let's go ahead and talk about this problem. What do you guys think is a good approach to this?
No, 7 subtracted by the area of the known graph.
Right, so -6 to 5 is actually the area of the entire thing. Not this entire thing, but the entire thing, even the part that we don't see, right? And then what we can say is, well, we can take the area of this whole graph and do 7 minus that area, and that will give us what they're looking for. What they're looking for is from -6 to -2, i.e. from something here, -6, all the way to -2, even before this graph actually started, okay? So let's write down the work first, and then we'll go ahead and get to it. This might be the only thing we do today, I'm not sure. So go ahead and write down that the area from -6 to -2 on the graph added to the area from -2 to +5 on the graph should equate, right, notice how this is one of the rules that we've learned about integration, should equate to the area from -6 to +5 on that same graph. You might, again, because you're going to look back at this later and be like, how did he figure some parts of this out? So you want to make little notes for yourself, okay? One of the notes that you want to make for yourself is that -6 to 5 is actually the whole area, and it's actually given to us, right? This is the whole area, it's given to us. Unfortunately, the whole graph is not given to us. The area from -2 to 5, we're going to find that. I'm going to have you guys spend some time with that today, and you're going to find the area underneath this graph. Notice how they're asking for the area under the F graph. This is the F graph. So you're going to get busy in finding all of these areas. And this right here is the question in the picture, okay? All right, so to the person who said, they said, I'll do 7 minus that, good job, that's the logic. Okay, so go ahead and get started. Remember, we always find areas between the x-axis and the graph. Okay, between the x-axis and the graph, all right? I'm just going to quietly do some work here, and then we'll talk a little bit. so again, let's take a look at this, right? The part that got a lot of students was that last part right there, okay? Because you don't have a technique to find the void between the bottom of a circle and the x-axis. So what a lot of people did is they thought that, oh, I'll just find the area of a quarter circle, but it's very tricky. The quarter circle is not bounded by the x-axis, so it's not what a lot of folks thought. So maybe you thought the same thing, and that's okay, right? It's in the beginning of the game here. But basically what you have to do is realize that, okay, first of all, are you guys good with this 0.5 and these 4 triangles? Yes, no?
Yeah.
Okay, how did you do it? I have some hunch, but how did you?
So I did the small one like how you did it.
Okay.
And then I did the second small one that's like across of it that looks like it kind of like a bow. And then I did a whole big one from the -1 to the 3. I made that one big one. And then I did just a quarter circle on the side.
I know, but it's, like I said, it's by the x-axis, it's relative to the x-axis. So you can't just find an area of this big triangle, you need to find that small triangle relative to the x-axis, and that small triangle right there. That's the only way you can do it.
So not even from like the -1 to the 3 off
No.
of that, right?
No.
Well, so I just ignore the negative to 0.
I was gonna say that, but I don't wanna like say, oh, you know, this I did in my head. I just wanted to first make sure everyone's got the 4 triangles good, yes?
I was gonna ask you about the last one.
Okay, alright, now let's talk about the last one. Okay, so remember, you guys, the area, if it helps for you to think about it, I don't wanna mark this up any more than it's already marked up. The area is always relative to the x-axis. Again, back to your remark, Jenna.
Yeah.
What you were doing is you were finding this massive area, but you're not finding it relative to the x-axis. This is the thing that cuts it all. This is what makes triangles.
Yeah.
So that's how you have to think about it, okay? Now, let's talk about that last area right there. Okay, that last area, if this is what you want, you have to run through a little bit of a logic that we learned in geometry. What you can do is you can find the area of a square that's a 3 by 3 square. If you look on the y-axis, that's 3 units high, right? So you know it's a square. Otherwise, it would have been a rectangle, all right? So you take that square and you find its area, and that area is 9. Are you guys good with that logic? Yes, no?
Yeah.
Then you know that that's not actually the thing you wanted. What you really wanted was the part of the circle that's not contained within the square. So you have to cut out this quarter of a circle. In order to cut out that quarter of a circle, what you need to do is find the area of a full circle, which would be pi times 3 squared, and then take a quarter of that, alright? So that's why I took 9 minus a quarter of that area of a circle. And then once you're done with that, I went ahead and I rewrote this equation. This is why I started off with something that was logical, so you wouldn't get lost and wait, what are we finding again? Yusuf said that some of these I didn't really even need them because here's what he thought. He figured this one and this one are supposed to cancel one another out. And even if you think a little harder, you'll notice that this one and this where my pinky is, they also cross off, you know? But then you'd have made a trapezoid out of that remaining space. So you're welcome to do that or not. It's totally, again, it really comes down to you, but here's what you'll have. This will make 2.25 and add that to 9, so you'll have 11.25 minus 9 pi over 4. No one's asking you to actually evaluate that as a decimal. You don't have a calculator with you. So you just throw all of that over to the other side. So you'll have 11 minus 9 pi over 4, and when you send it over to the other side, they'll switch signs. So the area from -6 to 2 of this function is going to be 7 minus the 11 plus the 9 pi over 4, and so you'll have -4 plus 9 pi over 4. That was an insane question. Usually the AP questions are not that difficult, but I had a pretty low average too. Quick question before we wrap up. Do you guys know how to find the area of a trapezoid?
Yes.
Okay, let's suppose I had made a trapezoid. Here, let me do it on the board here. I just gotta make sure everyone is solid with this. So if I made a trapezoid, in this trapezoid, what are the bases that we have? 1 and?
1 and 3.
And 3.
And what's the height of the trapezoid?
1. Yeah, that's it. Rabbit.
Okay, so notice that would have given you 2 as an area. And so if this is 2 as an area, then you would have still been putting all the rest of that together. Then you would have gotten 11, like I told Alright, yeah, we'll stop here.
I know, bro. I think she posted it at the end of the day. I won't be able to know, bro. Like, I don't open my Chromebook and then also I checked it. It's really have instructions. It says chapter 29, page number or instruction.